for the analytic properties of an S matrix, which is a function S of the momentum K. And in the complex K-plane, so this is a summary. So the basic message is that there are poles for purely imaginary K that correspond to bound states. These poles must have positive residue. Okay, thing number one. There could also be zeros, and the zeros, if they are close to the real axis, not at the real axis, but close to the real axis, we interpret them as resonances. They will manifest themselves when you study the wave function as some peaks of the wave function, like the Higgs. And so we detect them as some unstable particles that the wave function for a long time stays in some state with momentum approximately equal to the momentum of the resonance and then decays again. This is all there is for cases of type A, which are for ultra-local potentials. Then if we do these cases that are local but not ultra-local, the key difference is that at infinity you have this prescribed essential singularity. It's always the same, so we just memorize it once and that's it. It's e to the minus 2i ka if the potential goes from minus a to a. Okay? And it's always that essential singularity. And that's it if we are in case B, which was the case where the potential is local but with a finite range. And finally, if we are in case C, which means that it decays exponentially, or fast, or it decays exponentially, smaller or equal, the potential here is smaller or equal than e to the minus x over a. So a is, like before, some measure of the range of the potential, but now it decays exponentially. Then there can be, and there will be dragons, there will be this region above 1 over 2a. Again, if a is small, this is a big region, but above this region, there is some region where it's very hard to control what's going on. Okay? And there could be fake poles, like this tower that we found for the exponential potential, and there could also be some true poles, some true bound states there. But they will be in the mix, there will be brave poles that stand together with these dragons, and things are more complicated there. As I told you last time, I thought that we could sometimes slay these dragons. And we could slay these dragons, we could kill them by truncating the potential, right? So we could transform this potential into some similar potential where I cut off the tails. And I was saying probably this shouldn't change the physics, but it should kill the dragons. Okay? So I just did, I added yesterday this plot to the notes. I just want to show you. So if you go to the notes, oh, where are they? It should be, okay, slaying dragons here, good. Okay, so here it is. So we could consider this potential, which is the same as the exponential, except I make it 0 for some b much bigger than a. And then we can compute the S matrix for this potential. It's trivial. And here it's the S matrix, the real part of the S matrix as a function of momenta. You see, it's some function, it has some real part, and there are two curves on this left plot. And you cannot tell there are two curves because the curves are on top of each other. The two curves are the S matrix with B and without B. I put some B large. The numbers I put, it's A equals 7 and B equals 55. Okay? So there is some potential. It decays as e to the minus x over 7, and then I cut it off at 55. And then you cannot tell the difference. If you plot the difference, you can see it, but it's very small. If I zoom in, you cannot tell. But this number is 0.015. So it's like 1%, up to 1%, the two S matrices are exactly the same for real momentum, as you expect, right? If you scatter off this potential, or out of this potential, who can tell? I mean, this is e to the minus 55 times e to the minus 55 over 7, right? So it's super small. However, just doing this should kill the dragons. And so let's see if it does. So now here below I'm plotting two functions, the red and the blue. The red, you see, it's 1 over the S matrix, meaning that the zeros of this red function are the poles, right? Because poles are explosions of S matrix, I'm plotting 1 over the S matrix. And I just put some power 1 over 4 just so that the plot range is nicer. And then I do the same for the blue one, which is for the new potential. Okay? Now we don't go to real values, which is where we do an experiment. We go to imaginary values, which is where we measure the bound states. And the two functions were super similar for real values. Now in imaginary values, they don't need to be, right? And so these are the two curves that we get. So you see that the red curve, it has first this pole here, which is a bound state. And then it continues, and you have this red pole, and this one, and all these equally spaced red poles, they are dragons. They are in this red dragon region. They are not true poles. There are also some poles, some zeros of the red function, like this one, and also one very close to a fake pole that are true bound states. So there are 3 bound states in this potential. But these 3 bound states, they are in the middle of all these dragons. And then if you plot for the blue, you get this beautiful curve. It vanishes here, then it goes up, and then it has another 0 here, boom, another bound state. And then it goes up again, and then it goes, and then it goes down again, and it has another 0 here, which is the 3rd bound state. And so indeed, the blue wave function has no dragons, and it just has the zeros, the poles, exactly where the bound states, the physical bound states should be. Okay? So it's a very simple but cute exercise that you can do to slay these dragons. Yes?
Do you have an idea why the blue curve seems discontinuous at the zeros?
No, the question is, why does it seem discontinuous? It's not discontinuous. You just, this thing, that the curve does this. If you zoom in here, you see the curve is just doing this. It is just that it's a very well-defined pole, so it's really very sharp. There is a pole. If you zoom in, you see clearly there is a pole. But you have to zoom in, and you have to zoom in a lot, so it's very hard to see these zeros. I don't have Mathematica here, but if I did, I would zoom in and show you that you get, it's something smooth like this. So it's a pole of this matrix that is a 0 that just goes down very quickly. Okay, very good. So this is the picture we expect, and it's nice that we can see it. We just replace the potential of type C by type B, and indeed, we get the behavior we get, right? So it changes a little bit. For example, to plot the blue curve, you see I divided by the essential singularity. Otherwise, the blue curve is huge, because the blue curve now has this essential singularity e to the 2, which is universal, which is related to this size B here. And that's, again, what we expect. Okay? Here we are just caring about the zeros, and this we see them very nicely. Okay, now that we know the animal we are dealing with, this S matrix, now we can ask, what is the space of these S matrices? What can they be? Right? And the main tool we are using is this maximum modulus principle that says if I have a function that's holomorphic and bounded in the boundary of the region, then it's bounded inside the region. Right? So if you have a function, it's holomorphic in some domain, at the boundary it's bounded, then it's bounded inside as well. Okay? And the precise details was what we explained last time. Then we started applying this principle. First example was, suppose I have an S matrix without bound states. Then, at the boundary, which is the real line, it's smaller or equal than 1. Then it's smaller or equal than 1 everywhere. And so this S matrix, at some value in the imaginary line, is smaller or equal than 1. And 1 is saturated by the constant S matrix S equal to 1, which is the free theory. Then we move to a more interesting example, Bootstrap Problem 2, which is, suppose we have a single bound state with some coupling G squared that's positive. How big can this G squared be? And the answer is non-trivial. The biggest it can be is twice kappa, where kappa is related to the binding energy of the bound state. Okay? So that was the solution. Then we move to Bootstrap Problem 3. Also, you have a single bound state, but you are dealing with a potential of type B. And the bound became loser. It became that the residue is positive, and it's smaller than 2 kappa exponential of 2 kappa times A. So let me remind you how we derive this more general case that reduces to this as I take A to 0. You take your function f, which is not holomorphic because it has the bound state pole. And it's also not holomorphic, it's also not good to apply our theorem because it has an essential singularity. So we solve both problems. We divide by the essential singularity. So now this function has no essential singularity. And then we multiply by something that is 0 at the pole. And it has a pole in the lower half plane, so we don't care. We divide by this pole so that this full factor is a phase at the boundary of my domain. When k is real, this is a phase. And so this new function is holomorphic. It's bounded at the boundary of the domain, and so it's bounded everywhere, and so it's smaller or equal than 1 everywhere, in particular at I kappa, but at I kappa it's related to the residue, and therefore the residue obeys that equation there. Okay? Not only it obeys this relation there, but this guy is saturated for the S matrix where this F is equal to 1. So when this F is equal to 1. So it's saturated for S of K, but let's call it optimal. That's the one that has the biggest residue, which would be equal to e to the minus 2I Ka times the inverse of this, so K plus I kappa over K minus I kappa. And what is the theory that has this S matrix? Well, if A is equal to 0, it's the delta function potential that we saw before. What if A is not 0? Well, it's some potential. I actually don't know what potential gives it. So you see, it's an example where we got the S matrix. Now, if you really want to know the potential, you have to reverse engineer. You have to find what potential could give me this S matrix. Right? Maybe you want to know. Okay, then you have to use this technology that I told you existed. Given an S matrix, how do I construct a potential? I never did this exercise, so I don't know what potential gives this S matrix, but it's a physical S matrix that someone could measure. And if all you do is measure the phase shift, you don't know exactly what the potential is. It's something hard to measure, but this is more physical anyway, so this is, well, for some purposes, this is what you would care. Right? Good. So, let's move on, and now let's consider, like we promised, let's continue in these bootstrap problems, and let's first consider a simple one. So let's consider that we have a potential V of type A. I mean, A or B is just about this, putting this exponential. It's trivial, so I don't worry about it. So we have a V of type A. We have one single bound state. But let's suppose that someone experimentally measured, like the analog of the Higgs. There was a resonance that was detected there. So we know this theory, somehow, we did the experiment and we know there is a resonance. So we know there exists a resonance, and we know the mass and the width and the time life of the resonance, so we know it at some K equal to A plus IB. In fact, resonances, they always come in pairs, right? Because you remember that there was a reflection around the imaginary axis. So if these zeros are here, there are reflection zeros here. And so it would be, the resonance would be detected for positive or negative velocities. Okay, and then, so there's one bound state with some G-square coupling. Right? And now we could ask, what is the maximum, what is the allowed values of G-square? We know this residue is positive, and we ask, as usual, what is the biggest value it can take. So let's do this exercise. So just to practice a little bit, so it's very similar to what we did last time. It's just for us to remind ourselves. So what do we do? So we want to impose that this function, we want to use this theorem, and we want to know that the function, it needs to have these zeros at these two locations. So they have these zeros at these positions. Right? And it has a pole. Right? Well, then I could try to trivialize the conditions like I did here. So first we start saying f of k. Let me define it as being s of k, and I remove the pole. So I subtract k minus I kappa. Kappa is the location of the residue. K plus I kappa. And now this function is an holomorphic function, bounded, and so we know from this we could derive this bound on the coupling, right? By just evaluating that function at I kappa, right? But now we want to input that this function as a 0 at this location. That's the resonance, right? So let's put the 0 explicitly. Let's say that this S matrix has the 0 explicitly, so we can divide by this 0, right? So if we want to force this, we want this function as a 0, so we can remove it to say that this function is a general function. And so I subtract here k minus this 0, a plus ib, and I also divide by the other one with the other sign, k minus a plus ib. Now this function f of k, because I removed the zeros, this function now does not have zeros at these locations, right? Does not need to have zeros at this location. It had the zeros, I divided. Okay, if you want to have double zeros, you can still have, but you don't need, no. The function is free. But the problem with doing just this would be that at the boundary, this is a phase, and these guys are not phases. So we do the usual trick. We complete it to make it into a phase. So I subtract here k minus ib. So what am I doing? Now I'm saying this function as a 0 in the lower half plane. Okay, but that's fine. The lower half plane, we don't care. All we care is about not putting stuff that we don't know in the upper half plane. And similarly, we put here k minus a minus ib. Now, this function f of k it's just bounded at the boundary, and it has no singularities that we know of inside. Right? And so now, if I evaluate this function f at ik, this function is smaller or equal than 1. But this is equal to what? This just extracts the residue, so it just gives me g squared over 2 kappa, the first factor. Right? This, when I evaluate at I kappa, it just extracts the residue. G squared times I over this factor, this cancels this, and I get g squared times I over 2I kappa, so the I cancels and I get this. And then this factor evaluated at I kappa, which gives me this factor evaluated at I kappa, which gives me, let me try to do it, k I kappa, so kappa minus minus, it's plus, minus, yeah, kappa plus b square. Okay, let me write everything. A square, and here, down here, it will be kappa minus b square. The square. Did I get the sign right for a? Let's see. So probably no. Probably plus. Yeah, plus. Right? Do you agree with the algebra? I just evaluated this at I kappa. So at I kappa minus a plus a. So it's the square of the first one minus the second one squared, but there is an I. So yeah, it's correct. So let's see if this makes sense. So we got that g squared is smaller or equal than 2 kappa. But then there is a factor, a new factor, which is, let's write it and then hope that it came out correctly. K minus b squared plus a squared over kappa minus b squared, plus b squared plus a squared. So let's see if this makes sense. So kappa is positive, b is positive, a is positive. Okay, a can be whatever, but a doesn't matter. But a is real, b is positive, kappa is positive. Right? B is positive because it's in the upper half plane. Kappa is positive because it's in the upper half plane. And so kappa plus beta, kappa plus B is bigger than kappa minus B, and so the denominator is bigger, and so this bound is smaller than 2 kappa. This is smaller than 1. Right? And so this is the bound. The bound became stronger because we imposed that there is a resonance. Right? So you see this picture of this, the kind of things that the bootstrap is giving us. So we are studying the space of allowed couplings, and we get, say, the naive bound is from 0 to 2 kappa. Then we can, this is allowed, the rest is excluded. Right? Then we say, no, but there is a resonance. Okay, then the bound gets stronger. So this is A with resonance. This was just potential of type A. If on the other hand, we say, no, the potential can have some finite range, it can be of type B, then the potential became looser, right? It was this with this extra exponential factor here. Then it became a bit bigger. So this was type B without resonance. Then I can do B with resonance. So the bound can become weaker or stronger depending if you are imposing more physical conditions, relaxing physical conditions, and this is how it would go. Okay? So this is the summary of the kind of bounds we are exploring. And again, what S matrix saturates this bound is the S matrix, which is just the inverse of all this stuff. And you could ask again, what potential has this property? What's the potential which has a single resonance, right? Like a single particle that you detected, and a single bound state, and the bound state is as strongly coupled as possible. Okay, it's this S matrix, the product of these 3 factors. And now you could cook up what potential would generate that and try to create it in the lab if you really wanted to have a system with a single resonance and a single bound state. Okay, very good. So this was an easy one. And now, as I promised, we are moving to a tougher one today, which is 2 bound states. And it looks trivial, right? We are doing 1 bound state, we are putting a resonance. I mean, 2 bound states, who cares? I just keep going, and we will see it's a little bit more subtle. It requires thinking a little bit. Yeah, it's not really hard, but it's not as easy as this one's. So let's consider that. The bootstrap problem number 5, we have 2 bound states. Okay. We have an S matrix of type A with 2 bound states. Okay. 1 bound state at kappa with residue G square, 1 bound state at kappa prime with residue G prime square. Yes?
So when you did the second bootstrap, you you didn't restrict the S to not have zeros, and you reached a region which is smaller than this one. So I was trying, it shouldn't be that this region is inside of that region, that small region.
So this region is smaller. This factor here is smaller or equal than 1.
Yeah.
So this region is smaller than the region without imposing the resonance. Right? So what couplings are allowed in general? It's from 0 to 2 kappa. Now if you say what couplings are allowed if I further know that there is a resonance, now it's a little bit smaller. Right? So this factor is smaller than 1, so it shrunk the allowed region. Right? So the more things we know, the smaller is the region, right? Like in the exclusion plots we were seeing in the morning. Okay. So 2 bound states. So remember, the key thing about bound states, we already anticipated, is that the residue is positive, right? So let's first ignore this condition, because then it's trivial, and then we'll fix it. So if we ignore that the residue is positive, then it's as trivial as before. So if we ignore, then all we would say is if you have a function, and all you know is that the function has this reality property, right? That the function here is related to the function here, right? By symmetry. That's all you impose. And you impose that you have two bound states. Right? So the function has some real residue, but we don't impose positivity. We just impose that there is some residue. And we ask, this is kappa, this is kappa prime, and this residue is g squared, and this residue is g prime squared. And we ask for this function like this, these properties, and the function is bounded here. What is the maximum value of g squared? Right? And now, if I forget about the sign of residues, it's as we did before. We just will construct a function which removes the poles, right? And that is bounded at, and that is still bounded at the boundary, right? So if we can ignore this, we just do as before. F of k, we just define it as S of k, and then we remove the known singularities. K minus I kappa, k minus I kappa prime. And then, to make this into a phase at the boundary, I just put k plus I kappa, and I put k plus I kappa prime. Right? So I removed the poles, but I kept the property that it's smaller or equal than 1 at the boundary, because these factors have absolute value 1 at the boundary. Right? Do you agree? This is true. And so this function is smaller or equal than 1 at any value, in particular at I kappa. Right? And therefore, if I compute this at I kappa, same algebra as before. The first factor gives me g squared over 2 kappa. Right? This factor gives always g squared over 2 kappa. But the second factor would give me kappa minus kappa prime over kappa plus kappa prime. Okay. So this function is smaller than 1 in absolute value, so minus the function is smaller or equal than 1. I just put the minus sign because we know kappa prime is bigger than kappa. So it's still true. And so this factor needs to be smaller or equal than 1. And so we conclude that the maximum value of g squared is 2 kappa times kappa prime minus kappa divided by kappa prime plus kappa. No, the signs are opposite, plus and minus. And you see kappa prime is bigger than kappa, which is bigger than 0, and so this factor is bigger than 1. Right? And this means the coupling for these bound states, for two bound states, the residue of one of them can be now bigger than if the other bound state was not there. The problem, however, is that this is not good, because if I saturate this bound, then the S matrix is just given by this, right? By definition, right? So if you saturate the bound, the S matrix is given by the inverse of these two factors, as usual, right? But this will have a negative residue at the second pole, right? So how do we see it? We see this very easily because this function has a pole with positive residue, the one we maximized, but it has no 0 before the other pole, and therefore the second residue must come out wrong, right? So if I plot the function that optimizes this, if I plot S optimal as a function of k over I, so I plot it in the imaginary axis, this t in the imaginary axis. Right? If I plot this function has a residue that comes out right, the first one, at kappa. But then it has no 0 in between, which means the second residue for sure has the wrong sign at kappa prime, right? Because there's no 0 in between. So as I go there, if this guy was good, this one now needs to be wrong, right? Because there's no 0 in between, right? Do you agree? So it cannot, no, sorry. There's no 0 in between, so I should not draw the picture like this. Since I know there's no 0 in between, the picture is like Because there's no 0, right? This function, when I go between this pole and this pole, there's nothing. There's no 0 there, right? Right? So the only two zeros, these zeros are in the lower half plane. There is no 0 in the upper half plane. Correct? Is it? Yeah. Sorry? Yeah. Good. So the question is, so first of all, let's recognize that the problem is that this residue here, the first one is positive, but the second one is negative. And so this solution needs to be discarded. The solution is not good. It's a solution to the mathematical problem. Then it's true, then it's a correct bound. But this solution has a big residue here because it puts a big negative residue here. Right? In other words, it's like you have a big positive charge and a big negative charge that is screening it. And because of it, when you are far away from these two, the effective residue is smaller. So the two residues, they don't have the same sign, and therefore they are screening each other. Right? And if we impose that both are positive, then this doesn't happen. They cannot screen each other, and therefore the bound cannot be so big. Okay? Okay. So as was pointed out, the only way you can have the right residue is by putting a 0 in the middle. So if you want the function to be like this, and here as well, like this, then it needs to have a 0 here. It comes from minus infinity, it goes to plus infinity, it needs to have a 0 in the middle. Right? You agree? That for the function to have the right residue, it needs to have a 0 in the middle. Is this okay? Comes from minus infinity, goes to plus infinity, it needs to have a 0 in the middle. Okay, so then let's open a parenthesis and solve an auxiliary problem. So let's solve a problem Bootstrap 5 prime. So let's suppose the Bootstrap problem 5 is the same as Bootstrap problem 5. We have an S matrix of type A. There are two bound states. And we impose that there exists a 0 at some k equal to some IA with some fixed A that is between kappa and kappa prime. And then, with this, we ask, what's the maximum value of G squared? Okay, well, it's easy, because we have experience putting zeros. We just did it here, putting in this resonance, right? The resonance was a pair of complex conjugate zeros. But if the 0 is in the imaginary axis, that's the only case where I actually can put just a single one. Right? Do you agree? So we conclude right away that what we should do to solve this problem is define the function f of k, which is, or let me call it f tilde, which is that f of k of problem B5, the one there, and we put this extra 0. So we remove kappa minus IA, and we put here kappa plus IA. And now, again, this function f of I kappa, which is smaller or equal than 1, is equal, in absolute value, it's equal to that, what is written there. So G squared over 2 kappa times kappa prime minus kappa, kappa prime plus kappa. But now there is this extra factor evaluated at I kappa, which just gives me kappa plus A over kappa minus A, but there was an overall sign, so it's actually minus and plus. Is it okay? And so now this is the final solution, which is that this is the correct maximum coupling. If you know such zero exists, then this is true. And let me point out, okay, so here it's A minus kappa. Okay. Okay, so that's it. So that's the maximum value. And now we can solve the problem we want to solve for two bound states. Now we can go back to problem Bootstrap 5, which is to say we know that a 0 must be there. So the Bootstrap problem 5 is given by saying we should pick A that makes this as big as possible. So we just, the solution to problem 5 is just maximize over A. Just find the A that gives the optimal bound now. Right? Because now we know that the optimal solution has a 0. If you have a 0, then your coupling G squared is smaller or equal than the inverse of this. Right? And now you just find the A that gives you the best bound. Yes?
The last term is not like kappa minus A?
Here? No, yes, but here it was also the opposite, and minus times minus, so I flipped the sign of both. Okay. And so we conclude that this residue G squared is smaller or equal than the inverse of this, so 2 kappa times the inverse of this, so kappa prime plus kappa, kappa prime minus kappa, and then A minus kappa, A prime, no, A plus kappa. And now you want to maximize this over A. This is to be maximized in A. But that's easy because this function is just monotonic. This function is just monotonic. And the answer is that if you plot this and you ask when is this biggest, the answer is that the A optimal is just kappa prime. And so what happens is that you said there must be a 0 in between, but to make the coupling to kappa biggest possible, you send the 0 close to the other guy, so you shut off the other particle. Okay? So that's just the fact. Okay? And so you conclude that the best you can do is that G squared is smaller or equal than 2 kappa, which is obtained for A equal to kappa prime. So the final space, the solution that we find then is the following, is that if we have two poles, what happens is that when you have two poles, if I study the space and I measure here one pole divided by 2 kappa, and I plot here the other pole, the other coupling, G squared prime over 2 kappa prime, Then I conclude that the allowed space of theories is inside this region, where here it's 1 and here it's 1. This theory that saturates this bound here, A is equal to kappa prime, or very close to kappa prime. So it means that you have two poles, but the coupling to the second is very small to maximize the coupling to the first one. And here, A is kappa, meaning you have two poles, you want to maximize the second one, so you shut down the first one. Right? So because both contribute with positive residue, that's indeed what you expect. Both contribute with positive residues, right? And they have the same effect on the real axis. So if you want to maximize one of them, it's best to shut off the other one. If they have negative residues, then no, then they could screen each other. But because they are competing, to make one big, you turn off the other. To make one big, you turn off the other. And so this region here is excluded, the region here outside. So this region here is excluded. Yeah?
Can you exclude more than this region? Because you cannot have like the other vertex.
Great. So the question is, can we solve now the problem of not just exploring the maximum of this guy or the maximum of this guy, but really asking, what is the allowed space, combined space, right? What is really the honest allowed region, and can we do better than just this, right? So the question is, can we find something like this? Right? That would be more interesting, right? Which would be, this would be better, this would be the optimal bound. And then we would also exclude this, right? And the answer is that to this region, to find this region, the claim is that the S matrix that does it is precisely of this form here. This same S matrix, the optimal S matrix that was parameterized by A, not only saturates the optimal bound in G square when you turn off when A goes to kappa prime, or the one here when it collides, but it describes the full region. Okay? And this is how you could get a beautiful allowed region separating allowed here inside and forbidden and excluded outside. Is this clear? Okay, good. So let me note that in this toy problem here, like we said, this factor is bigger than 1, so that this coupling is bigger. But that was because it had the wrong residue, the other one, right? So we made this coupling huge because there was one nearby that had the wrong sign. Do you agree? That was what was going on. You could ask the problem of, yeah. So let's try to now solve the following bootstrap problem, which is, now let's try to think of bootstrap problem number 6, which would be one bound state for a potential of type C. Okay, so we have dragons. Okay, now I'm not sure of what I'm going to say now. I'm not positive. Dragons is complicated. I'm going to speculate about what's the answer to this problem. I think it's probably correct, but let's see it together. Okay? It's tougher. Okay, so we venture into the dragon region. So before, let's think a little bit about this problem where we will maximize this coupling. We got this result, but we know that what happened was that this guy had negative residue, and so it was screening this one, allowing it to be bigger, right? It's like a bodyguard that is protecting this guy here. And so we could ask for the following problem. Suppose we have 3 bound states, 3 poles, and we want to maximize the closest one, and I don't care about the sign of the other 2. So like this, but instead of having this guy to screen, I have 2 guys that help me screen. Is it okay? So now what we do is we consider the toy model first, where I have this G square, and there are 2 more poles. And these ones, so this is the one we want to maximize. This is the one to maximize. And these are, if you want, screening poles. They are going to help me by creating some invisibility cloak. They will have negative charge, if you want, and screen this big pole. Okay, and now we ask, with 3 poles, what's the maximum coupling you can have? Okay? So, okay, I realized something. Yeah, it's interesting. Okay. Okay. I don't want to proceed further. I realize I don't know the answer to this problem. I don't even have a conjecture for it. Yeah, if there are dragons, they win. Okay. Okay. Wills. I don't want to continue. Okay, very good. So this is basically what the Bootstrap is a way of starting to explore regions. The regions we explored were just segments, except for this one where we said that just with this S matrix that has 3 factors, I could a priori plot this line and separate allowed from an unallowed, and now it starts to be really a region. We could get nice regions in that are even 3-dimensional regions if we start studying various points. For example, we could, let me just show you one picture. Let me define what this is and show you, just to give you an idea how simple mathematical problems can have quite non-trivial, can generate quite non-trivial looking shapes. Suppose I want to study functions that are holomorphic inside the unit disk. So this is a function, and the absolute value of f is smaller or equal than 1, and the function is holomorphic inside. Okay? And now, what I want to do is plot the allowed space, and let's do it a 3-dimensional space, because we love seeing 3D stuff. And so all we do is plot the 3-dimensional space, where here we plot x, which is the value of the function at the origin. Here we plot y, where y will be the derivative of the function at the origin. And here we plot z, where z would be the second derivative of the function at the origin. Okay? We say that this function, let's say that this function has this reality transformation. In other words, for real values, the function is real. So that the derivatives and functions at the origin are all real numbers. Let me first point out, before I show you the 3D result, that this problem is very closely related to what we are doing. We are doing things in the upper half plane, but by doing a conformal transformation, I can map the upper half plane to a unit disk. The transformation is in the notes. It's often useful. And then I study the unit disk. And then it will be like asking what is the space of S matrices at some point and the derivatives of the S matrix at that point. So you could translate it to a problem about S matrices. And now you would ask, what is this three-dimensional shape? Right? We know, for example, that f of 0 can be at most 1 and minus 1, right? So the 3D shape will be somewhere between this minus 1 and plus 1 line. Right? So it will be some 3D shape in between these two. But I can just show you a picture of what the correct, oops. Tiago, help me. I don't have the password. Okay. So while Tiago comes, then I'll just conclude this regular part of the lectures by showing you this plot. Let me now, this concludes the official part of the course, but in this remaining 20 minutes before we go into the questions, I would like to give you a brief overview of how this S-matrix bootstrap that we discussed now would lift to the space of all quantum field theories, and how we would go from this Schrödinger equation to relativistic quantum field theory in 2 dimensions to relativistic quantum field theory in higher dimensions. So just to give you a brief bird's eye view of what's going on. Okay. Oi, Tiago. Podia só abrir ali o password, não sei qual. E pode-me abrir um browser também? Eu preciso de abrir um paper. Já está no browser? Não, tá bom, obrigado. Okay, so let me show you the space. This space, it's a cute space. So this is just a solution to this problem, these 3 x's. But you'll see. Suspense. Okay. So this was a paper where we were studying the space of S matrices for flux tubes in chromodynamical flux theories, but in the appendix we do some complex analysis for fun, and you see this is the allowed space. You see, it's a cute space. You could you can find it analytically, but it's quite an untrivial shape with some edges and so on. It will be a nice shape to 3D print. You see, it's really the solution. Just this: you have a holomorphic function bounded inside the disk. What's the space of the function and the derivatives? And it gives this beautiful 3D shape with these lines and so on. That is drawn here. Okay? So it's the intersection of some simple equations. Yeah. Okay. So very good. So as I said, this concludes this general bootstrap for slow one-dimensional beings. So let's discuss a little bit what would happen if we would go beyond this limit. So first of all, let's think a bit what would happen if I think not in terms of momenta, but in terms of energy. So that's very simple, right? So all we do is we translate energy to momentum. Energy is just k squared, right? So you see that here, k positive and k negative are mapped to the same energy, right? And k equals 5 squared is minus 5 squared, right? And so in the energy plane, we have a cut, and the values, this stuff would be this part, and this part would be below here. Right? All we do is we write k is equal to square root of e. Right? So let's just put right here one S matrix to have in mind for the delta function potential. This S matrix would be square root of energy plus I kappa over square root of energy minus I kappa, right? So this function clearly is a function of the energy. It has a cut for positive energy. And then there were these poles at positive imaginary kappa that now correspond to negative energies. So this negative energy is just the binding energy of the bound states. So now we have these poles here, and these are the bound states. And then we have the resonances. If we go in energy, we have the resonances that are now here. And these are just the resonances. Right? So the 126 GeV is the Higgs. Right? These are just the energies. Okay, so this is the picture in E. So we have this cut, we have the bound states here, and we have the resonances here. What we do in going from E to K, we say we opened up the cut. We chose variables where we resolved the cut. And now the cut doesn't exist in this smarter variable. Okay? Yes?
What does it mean to the energy having an imaginary part?
The energy is negative, right?
No, in the resonance.
The resonance, the energy having an imaginary part means it has some lifetime. I mean, very schematically, so first of all, we saw it in the box, right? The wave function stays for a long time inside the box and then disappears. Heuristically, you can think that if your energy has some imaginary part, then its evolution, right? The time evolution would look like e to the minus ti times the mass, if the mass is the real part of the energy, and then minus t times the imaginary part that I write over t, over tau. And so the imaginary part would have the meaning of how fast it decays.
So it's like a damping.
Yeah, it's like an unstable particle, so it has some lifetime to decay, and it has some mass that gives the energy of the particle. Okay, very good. So that's the picture in the complex plane of E. Now, and furthermore, let me remind you that the S matrix was a function of K1 minus K2, which was what we called K, which is also square root of E. And this was the fact that it only depended on the difference was a consequence of Galilean symmetry, which is a fancy way of saying we have translation invariance, and therefore things depend only on the relative velocity. So now let's think what happens if we were to do things relativistic, where now we have Lorentz invariant instead of Galilean invariance. So let's think of the scattering experiment relativistically now. Okay, so we have two particles going in, two particles going out. So the particles come in, and each particle has its own energy momentum. This is momentum 2. This would be the energy momentum 1. And this would be the energy momentum 4. And this would be the energy momentum vector 3. This energy momentum is the usual 4 momentum, except that now it's 2 momentum because we are in 2 dimensions, right? And so this energy momentum is what? It's something like, if here I have the momentum P, okay, this is, for us is just a number because we are in 2 dimensions. If we were in 3 dimensions, it would be a 3 vector. Then here we have something like square root of m square c to the 4 plus c square p square, where this now is the energy. And then if you compute k square, which in this notation that I'm writing would be the first component of the vector square minus the second component with some c for units square, then you get that this is just equal, this minus this, this term cancels, and we get just the famous expression for the energy of a particle at rest in the center of mass square. Right? So this is the usual energy that of a particle of mass m, right, at rest. Okay, good. So this is the parameterization of our momentum. And of course, this energy, when the speed of light is huge or when the momentum is much smaller than mc, the square root is just mc squared, this energy of this particle in this frame, plus p squared over 2m plus dot, dot, dot. Okay? And this is the energy that we were using in our Schrödinger problem. Now, so we have these vectors, k1 and k2, and then we have energy momentum conservation. This just tells me that the sum over all this momentum k mu is equal to 0. This tells me that energy and momentum are both conserved. And this tells me, and all these vectors are on shell, which means all these vectors obey this condition. So all these vectors are just parameterized by each one by one number, right? And so we have two numbers here, but we have two conditions, the energy and the momentum, so it fixes completely these vectors. And the scattering is just elastic, like we said before. This is the same as in the non-relativistic case. And this implies that this vector k3 is just minus the vector k2, and this vector k4 is just minus the vector k1. Oh, just the vector k3 is just a continuation of k2, k1 is just a continuation of k4. Okay. And what is k1 plus k2 squared? These two vectors. Now, what is k1 plus k2 squared? Where square is in this sense. So this is what I call just k squared. When I write k squared, I mean take the vector and square it k mu with the appropriate c squares. Then this, right, in the same way that for a single particle, we just get it, this, which is the energy of the particle in the center of mass. For two particles, right, k1 plus k2 squared is the center of mass energy. Is it clear for everyone? Why? Because it's Lorentz invariant, and when I choose p and minus p, the sum of the two just have energy components. Right? And because it's Lorentz invariant, once I can go to any frame to compute it. So this quantity is just equal to the energy in the center of mass squared. And if I compute it, then I would get that this is equal, if I go to the center of mass, to what? To 2mc squared, the energy at rest, plus k squared over 2m, which is the energy, plus dot, dot, dot. So we'll go to the center of mass, where p1 is just minus p2, where this spatial momentum is just a number. Okay? Is it okay? Now, this S matrix, this here is Lorentz invariant. And so the S matrix would be a function of this energy, like it was in the non-relativistic setup. So the S matrix, this quantity is what is normally called S. Our S matrix S is a function of S, where S up to a shift is just the same as before at low energies. It's just our k squared. So up to a shift, it's not different from our energy over there. However, when we have this scattering experiment, now we have relativity. We can look at the experiment from here, or we can look at the experiment, if you want, from here. Right? So I thought of k1 and k2 as being my particles, but I could think of k1 and k3 as being my particles. And then these two would be the final outcome. And this is something I can only do when I'm doing the Lorentz invariant case. When we don't have Lorentz invariance, you cannot do this. Do you agree? And so, instead, you could consider T, which you would define as K1 plus K3 square, which is just K1 minus K2 square, because K3 is minus K2. And this would be the energy in the center of mass in the other channel, in what's called the cross channel. Okay? Now, what is the relation between S and T? So S, this has a minus sign, this has a plus sign. Right? Now, what can you see a relation, right? Can you write a relation between these two right away? So they're not the same. One has a minus, one has a plus. We know these vectors have the property that the square of these vectors is a constant. It's m squared. So what can I do with these two quantities to find the relation between them?
Sum these squares.
If we sum these two quantities, the cross term cancels, and the other terms are constants. So these S and T are not independent, but they obey a nice equation that T is just the squares, the sum of squares, but the squares just give m squared 4 times. So it's 4 m squared c to the 4 minus s. Do you agree? And so this function must have the following property, that if it's true that I can look at the function from both sides, if I have this function s of s, this function should be equal, if I tilt my head and I look at it from the side, to the S matrix. When I have a relativistic theory, I should have an extra property that I can replace S by T, and this crossing symmetry becomes this property here.
That's the replacement of the evenness of the function.
That's just what replaces looking it from this side or from this side. It's not about even, no. We'll see in a second what it is. And so this is what's called crossing symmetry or Lorentz symmetry. But we call it crossing symmetry because it amounts to swapping time and space, which is a relativistic property we can do. And it tells me that the relativistic S matrix has this extra property here. Okay? Now, okay. So what does it mean? It means that the relativistic S matrix, the properties of the relativistic S matrix are the following. Here we had this energy and we had this cut, and now we have these bound states here. Right? So now we can see that in S, we will also have a cut. The energy starts being measured not at 0, but it starts being measured at 2mc squared square, which is the rest energy. That's just a shift. That's not very relevant, but if we plot it in the complex plane, let me plot it in the complex plane, S minus that rest energy. Okay? Then I have a cut in this variable that starts at 0, like for the energy there. And in fact, this quantity in the non-relativistic limit is the energy. So it's exactly that cut there. Okay? Then we could have some bound states, some weakly coupled bound states that have some small binding energy here. But then we know that actually 2m square c square away from here, there is a line. And then things are reflected with respect to this line. And so in the relativistic case, I have another cut and another set of poles that are reflected here. And I have another set of poles and an image cut. In this variable, this cut starts at minus 4m squared c to the 4. And these poles are what we call the T-channel poles. And these guys are what we call the usual poles, or if you want, the S-channel poles. So what's happening is the following. So here we are assuming that these particles are identical and it doesn't matter how I look from it, and therefore there is a perfect symmetry. Now, you could imagine maybe a more physical example would be when you scatter, for example, electron against electron. Then electron against electron, in one channel, it's electron against electron. Seen from the other side, it's electron against positron. So it's a different process that is related by flipping your head. In one case, you have electron and positron giving electron and positron. And in the other channel, you have electron and electron scattering by each other. Okay? That's because the electron is charged. Here, because we are thinking of a neutral particle, doesn't matter. It's one process, and from here, the same process. And so we have a symmetry. What's happening here, which pictorially we draw things like we form a resonance, and it evolves in time, and it decays, etc., is equivalent to what happens here, where things happen like this, being exchanged instead of being produced and annihilated. Now, you see that these poles have some positive residue, we know. But these poles are just the image of that. But this image, you see that this function of S is equal to the same function with a minus sign here. So if this pole has positive residue, this pole has negative residue. Right? So these guys have negative residue, these crossed poles. And this would be the picture when you go relativistic. Now, why don't we see it? Because the speed of light is huge, so this energy is huge, right? So if we are dealing with daily energies, we are not dealing with energies comparable to mc squared. And so what happens is that normally we are zooming in this region here, and all this stuff is infinitely far away. And so we are just looking here, and therefore we are just seeing this. We don't see that here there was some other stuff going on. Now, this was because the particles were very weakly bound. And so I had the particles of mass m and then some bound states that are not, the binding energy is not comparable to mc squared. Right? So the binding energy, by assumption, was much smaller than mc squared. That's what it means to be non-relativistic. The energies involved are much smaller than mc squared. Now, we could imagine a situation where there is some bound state that is not non-relativistic. So this would be a relativistic bound state. And then there would be a bound state with negative residue here. Let's use some different cross for negative residue. This would be a very light particle, right? It has a very big binding energy. So this would have an energy, it's still a heavy particle, but the binding energy is huge compared to this one. And you could even have a particle that is on this side. You could even have a particle here. This has a huge binding energy, all the way up to here. But now it would manifest itself as a bound state with a negative residue here. So what's going on is that this particle now is a really, really light particle. If you compute the mass of this particle, it's very small. And because it's a very small particle, you should integrate it out. And now you get a long-range potential because you integrated it out. And when you integrate out and you have a long-range potential, you have dragons. And so this is a dragon now. It's showing up in our non-relativistic setup as some pole with some negative residue. Okay, that's because there was a particle here that we integrated out and we only see our non-relativistic corner. So there was this line, and then here there would be some kind of dragon region. But here it's not a big deal, because here we know the full complex plane. We know here all the poles, some are positive, some are negative, and we can control them all. And so when we do the relativistic case, we control these dragons completely. We know if we allow for a local quantum field theory, there are positive and negative poles, and that's no big deal. They are just S and T channel processes. And it is just that the boundary now, our lab, is not just here. This was before our lab of positive energies. Now the boundary of the space is here and here. This is also our lab. And our boundary is bigger, but we have dragons and we control the dragons. Right? And these two labs, again, in the experiment of the electrons, one lab is doing the experiment, electron-electron goes to electron-electron. The other lab is doing the experiment, electron-positron annihilation, producing electron-positron again. Okay? And, okay, they are related, and if we control both, then we know the function is bounded here, it's bounded here. If we can argue there's no essential singularity, it's bounded everywhere, we can have poles of different sign, and that's fine, and now we can control it, and both have physical meaning. Okay? If, and it's the last sentence I'm going to say, this is the relativistic case in 2 dimensions. You have a function, and you have positive and negative poles. You have crossing symmetry that now relates the left and the right. And you have this single function of this energy. And then you could do higher dimensions, still non-relativistic. And now things don't depend just on the energy. They depend on the energy and on the scattering angle. And what you would do is you would trivialize the scattering angle by going to momentum space. Exactly like John Woo was describing in the beginning. When you study the sky, it's best to decompose the picture of the sky in angular momentum modes, because then you solve the angular momentum, right? Angular momentum is conserved. So if you go to angular momentum bases, they decouple, because angular momentum is conserved. And so what happens is that now, instead of one S matrix, we will have infinite S matrices, one for each spin. One when you prepare an S wave, one when we prepare a P wave, one when we prepare a D wave, etc. And now we will have to solve the problem of studying the space of infinitely many coupled S matrices, the S wave, D wave, P wave, etc., all these angular momentum modes that are not independent, because under crossing they transform under each other. Because then the expansion of these modes in one channel must be equal to the expansion of the modes in the other channel. And now this type of problems, you cannot do it analytically anymore. So everything we did was analytically, now you would have to do numerics. And the way these numerics go, and we didn't have time, but it's in the notes, the way they typically go is you parameterize functions, which have all the right properties. You try to do it with a big ansatz so that you believe you capture any function. And then you just do maximization on the space of all possible functions, imposing the physical constraints. And you let the computer find what the optimal solutions are. And then you check numerically in these cases that you can solve that the optimal S matrices are given by this or by all the guesses we have when you have guesses. And when you don't have guesses, then the computer's answer is the final answer. And in this way, you study the space of theories in higher dimensions. Of course, that's a big thing that is going on now. That's what is called the S-matrix bootstrap. And this is how, eventually, it connects to our case. First, we don't have spin because we are in one dimension. Then we don't have two cuts because we are doing non-relativistic. And if we zoom in here, we go to this picture where we have a single cut with its resonance, a bunch of bound state poles, and sometimes some dragons if the ignorance about the UV is sufficiently long range. Okay. So that's the total picture. That's over. Okay.
So is
Okay, we can go to questions now.
Is this reflection due to the symmetry of S and T related to some kind of supersymmetric particles?
No. No, it's related to particle and antiparticle. So what was before a particle going to the future, we can swap our head, and now it's a particle going, instead of going to the future, going to You can change the sign of time, who goes to the future, who goes to the past, and interpret things. It's just Lorentz symmetry. So there's nothing about supersymmetry in what I said. No, supersymmetry would be something else.
Does the U channel contribute to something that's interesting or not?
Okay, so the question is, what about the U channel? So you see that here, K4 is minus K1, and therefore U is equal to 0. So that's a property in 2 dimensions. In 2 dimensions, you don't have U. You only have S and T. In higher dimensions, and because you don't have U, you don't have momentum transfer because you are in the plane, and therefore the momentum is conserved. There's no transfer of momentum. There's no U. There's only S and T. And crossing symmetry relates both. So in the end, you have one variable. In higher dimensions, you still have a relation, which is S plus T plus U equal 4m squared. But now U is not 0, and so you have 2 variables. And the 2 variables are the energy and the angle. And that's why we need to decompose the angle by going to angular momentum basis by going to the angular momentum. So the angular momentum is the reflection of the fact that in higher dimensions we have energy and angle. In other words, we have S, T, and U plus a constraint.
Can you also obtain other properties, like you only obtained upper bounds of G squared? Can you obtain like minimum bounds, or can you give an example of like some kind of theory that you excluded by properties of the S matrix bootstrap? Like some real example in your research about that?
Yeah, so let me give a concrete example. So for example, this point here in the origin of the K-plane is what you would call the low energy point. The energy is equal to 0, right? So expansion around this point is expansion at low energy. And so you can take some theories and expand them at low energy and start seeing how they behave at low energy. And these theories, for example, could be gravity. And you could have that low energy, they behave like Einstein gravity, and then there is some deviation from Einstein gravity. Or they could be, for example, the theory of flux tubes there was this paper about flux tubes. And then the leading theory that describes chromodynamic flux tubes is what's called the Nambu-Goto theory, that describes the theory of the string that connects a quark and an antiquark. And then this theory has corrections. And now, using these techniques that we are describing in these lectures, we can ask how big or how small can these corrections to the leading theory that we have at low energy be? Okay? And so, for example, if you have a flux tube and you have a tube that is a quark, and there are some ripples of your flux tube between the quark and the antiquark. So this flux tube is a tube of energy between the quark and the antiquark. Okay? It's what keeps together the quark and antiquark. And then there is some scattering. You can send these particles against each other. And you can ask, what is the scattering of these particles as a function of the energy of these particles? And this object, S of K, S of S, is something that starts with S. Here I'm setting to 1 whatever constant is here. This sets my units. And then the first correction turns out to be I gamma S cube plus dot dot dot. And so this gamma is the first correction to the theory, to the fundamental theory of long strings, which is the Nambu-Goto string. Right? So you measure some effective string in the lab, or you do some lattice simulation, and you will always get S to be the leading behavior, and then there will be a correction that is gamma S cube. And this now, for example, what we showed in that paper that I was flashing to show that 3D plot is that gamma needs to be bigger or equal than minus 1 over 768. So that's it. And this is some number. It's 0.0013 or something like that. And now people are doing measures of lattice simulations to try to see what are the values of gamma that we measure in the real world. In SU2 gauge theory, in SU3 gauge theory, in Z2 gauge theory, in many theories where you have this It could be a cosmic string. It could be anything. Any object that's like a string, the claim is that the correction to the leading Nambu-Goto behavior needs to be bigger than -1/768. So it can be negative, but not very negative. Okay? And for example, it was observed that there is some Z2 gauge theory. It's not yet published, but some people claim it's very close to saturating this bound, and it seems to be the best so far. And so this gives you an example where we are starting to put a bound on the space of values. And now we are trying to study the theories to see which ones are close to the boundary, which ones are not. So for example, Monte Carlo is, for that theory, is giving values comparable to this bound that we put with some error bars that would be outside the bound. So those error bars are excluded, of course. I mean, this is a rigorous bound. And so that, I think, is the simplest one. So the theories that we have been using, trying to put bounds on, are flux tubes, pions, and gravity. And of course, gravity is very hard to do experiments. Pions is easier, but a bit dirty. And flux tubes is the easiest one because you can do more easily lattice simulations. And these are 3 examples of theories that are strongly coupled and that you don't have many other tools to study. And yeah, so that's an example of something concrete that you can do.
Thanks.
Is there something interesting that this relativistic picture can tell us about resonances?
So the question was if we gain some new intuition about the resonances by thinking about the relativistic theory. For most people, yes, because most people are used to thinking about relativistic quantum field theory. So immediately start drawing Feynman diagrams, doing perturbation theory, and but I think that's just because you have to click the button for a while until it's green. That's just because we are technically more used to doing Feynman diagrams and perturbation theory for relativistic theories that more easily we identify, oh, this is going to be a resonance, an imaginary part is going to come from this and that diagram. I think people that are used to quantum mechanics, no, they will get more intuition from here. But there's nothing deep that you learn physically by doing relativistic, I think.
Well, I have a question about the number of bound states on any potential. We have derived an equation that gives us the number of bounded states in a potential that is finite.
Yes.
My question is if there is possible to generalize this equation to any kind of potential. It could be, for example, a Gaussian potential.
Right. Okay, excellent question. The question is, if I have a given potential, how do I know how many bound states there are, right? So there are ways of doing what is called a semi-classical quantization, which is you study you take a particle inside the well, and you consider the momentum of the particle, and you let the particle go to the wall, bounce on the wall, and come back. And you ask that the total momentum integrated from one point to the other is a multiple of an integer. That gives a very good approximation, usually. Not at the very bottom of the potential or at the very top, but in most of the potential, it's very good. And so using that, then it tells you that the semi-integral of the momenta tells you more or less how many states there should be. So what I would say is that, yes, if you use Bohr-Sommerfeld quantization, it's the name that this goes by, you can have an estimate of the asymptotic growth of potentials. Now, if you want some integral that you do with some potential that tells you this potential has 13 bound states exactly, I don't know how to do it. I don't know if such thing exists. If it's possible, just look at some potential and tell this will have 8 bound states.
Okay, thanks. And just a little question. This number of bounded states should depend on the mass of the particles?
It depends. So the first thing we did in this lecture was roughly set m to 1. So we are implicitly measuring things in units of the mass of the particle. So, right, so when we say kappa, so our equations never had units, right? I was plotting things, I was saying things like kappa is 7 or a is 7, right? It's because I already set units by replacing h bar, m, etc. by 1. So if you want, you can put it back. In some of the problems, I ask you to put back, right? And then, yes, what will appear will not be V0 or kappa or H bar, but appropriate combinations thereof.
Yes, I'm asking this because on the potential well that we have worked, there is no dependence on the mass, but since we have equal to the kinetic energy to the potential, I was like, where's the mass?
Yeah, in that problem, I had a typo that I fixed it yesterday. So I think maybe, when did you see this problem with the M was missing?
Well, I have printed this.
You printed less than yesterday?
Yes.
Before yesterday? Yeah. Yesterday I fixed there was a mass missing in that problem. One of your colleagues pointed out that. Yeah. You have to click and wait a few seconds till it becomes green.
It's working. So when we derive for a two-bound state problem, and we find the SK with still a pole, why could
with what? With
it still had one pole.
Right. So we did it for two bound states, but we saw that to maximize the coupling to bound state 1, it's better to make the coupling to bound state 2 very small, or 0.
Yeah, but it's like when we first try to just multiply and see what's happening, it in the SK was left one pole. So I want to ask, why couldn't we, from this S matrix, we create another one like we did for the one bound state problem?
Sorry. So let me first see if I think there is something you said that I'm not sure is true. So you said that we had two poles, and then we did two things. One thing is we did not care about we only cared about maximizing this one, and we did not care about the sign of this one. That was the first thing. The second thing was we cared about both signs.
Yes, but it's when we try to solve this problem using the same method that we use on the other bound states problems.
Yeah, then the first step was we removed both poles.
Yeah. And
that's true.
And the SK was left with one pole, right? When the G square.
If you divide by both poles, the function we get has no poles.
Yeah.
It has a 0 pole.
Then we apply to one of the poles, the value of K. And we left with another pole of kappa prime.
Okay, let's do this more slowly because this is important. Okay, so the claim is that if you have two bound states, then the S matrix, which is the optimal S matrix, the one that would saturate the bound, will be equal to the naive one, which has a pole at k minus I kappa and k plus I kappa, times a factor k minus I kappa prime k plus I kappa prime. This was the naive guess. But the proposal is that it's three factors. It must be three factors because we must have a 0 in between. So here there is a k minus IA and k plus IA, where A is between kappa and kappa prime.
Before setting the 0, it's we try to apply for k equal E kappa, right?
Yes.
And then we left with k minus I kappa prime.
You're right. So those are numbers, right? They are not functions anymore of k. This is kappa, right? Okay, so good. So let's write here. So this is true, but you are saying that without Okay, maybe let me see if I understand. So without A, then the G square maximum at the pole, because G square maximum was 2 kappa divided by kappa plus kappa prime over kappa prime minus kappa, right? So all these are kappas, not k's. Right? And now you are saying this explodes when kappa and kappa prime are very close to each other.
Yeah.
So this is exactly this physical meaning of screening, right? Imagine I tell you, you have a pole, you have 2 poles on top of each other, one has positive residue, one has negative residue. How big can the residue be? It's infinity, because they're on top of each other, right? So it's like A minus A over X. Okay, A can be 1 million. If it's 1 million minus 1 million divided by X, you don't see it. So as these poles are approaching each other, if one has negative residue and one has positive residue, they can be huge because they are screening each other. Right? It's like a dipole that is very close, but one has positive charge, one has negative charge. Fine, I don't see it. Only when I look very, very close. So as they become closer and closer, the screening is better and better, and the residues can be huge. So it's physical, this thing here.
All right. I think I understand the problem now.
Yeah.
Thank you.
Oh, no, welcome.
Hi, could you elaborate on how you've obtained the space of F functions that are holomorphic inside the radius 1 disk?
Okay. We can do it. It's fun. Okay, so the question is, how did we plot this nice 3D shape that looks like an Apple product, right? Like this, this thing that you want to 3D print. So
It's a pastel.
yeah, so yeah, this beautiful 3D shape and so on. How could we get it? And the idea is to promote this maximum modulus principle to something that's called the Schwartz peak lemma. Or we can... This is a cute piece of complex analysis, so let me tell you. And the idea is the following. We have a function S of k that is, or let's do f of z. We have a function f of z that is in the unit disk and it's bounded, right? So mathematically we say it's in the unit disk, it takes value in the unit disk, so it takes value in the unit disk. And where do these values go? Well, f is smaller than 1 everywhere. That's the definition of unit disk again, right? So f is function of unit disk to unit disk. Okay? Now we say then the following function, which we call f with an index 1, is also, and I will define, is also disk to disk. And now I'll tell you what F1 is. Where f with index 1 is the following. The first thing you do is you take f of z and you subtract f of w. W is a parameter. So this function is a function of z, and it depends on the parameter w. Now, like this is not true, what I'm saying. But now I divide by 1 minus f of z, f of w conjugate. Okay? The claim is that this function is unit disk to unit disk. It's very easy to see, so don't be afraid. So all you have to see is, first of all, I'm dividing, but I'm not introducing any singularity, because this is smaller or equal than 1. This is the conjugate of something smaller or equal than 1. So when I'm inside the disk, 1 minus this is never 0. This function has a 0 when z equal to w. Okay? So I can divide by z minus w, and then I put here 1 minus ZW bar. W bar and f of W bar, it's okay, because W is a parameter. The function is holomorphic in Z, not in W. In W, no. There is W bar explicitly here. There is f of W bar here. But this function, as a function of Z, it's disk to disk. Okay? So the way to check it is, this is a phase at the boundary of the disk. You can check, because this is complex conjugate, and Z is 1 over Z when you are at the boundary of the disk. The conjugate of Z is 1 over Z. And then you can check that this is a Mobius transformation, and this function, if f and f are both smaller than 1, this function is smaller or equal than 1. Okay? It's a simple exercise to check. Yes?
Is this like Lorentz addition of velocities?
It reminds Lorentz addition of velocities, yeah. It looks very similar, right? V minus V over 1 minus V over C squared, yeah. It does look like it, yeah. Okay, now this combination is disk to disk, right? And so now you can set W, you send to Z, and what you get, when W goes to Z, you get that f prime of Z divided by 1 minus absolute value of f squared when you send W to Z. So this ratio over this quantity, this ratio over this quantity is just a derivative times 1 minus Z squared, absolute value, is smaller or equal than 1. Right, when you send Z to W. And now if you set Z equal to 0, this goes away, and you get that f prime of 0 is smaller or equal to 1 minus f of 0 squared. So that's the that's one equation. F prime is smaller, for any function, f prime is smaller than this. Right? But now that you constructed this, nothing stops you from continuing. Now you can just define f2, which is the same with f replaced by f1. And that's what's called the Schwarz derivative, this procedure. You get some generalization of derivatives. You got the first derivative, and now you'll get the second Schwarz derivative, the third Schwarz derivative, and so on. And now that the second one will give you access to the second derivative of the function now. And that allows you to do that 3D shape that was there. Then by just computing this, sending Z to W, and then sending Z to 0. And in this way, you get the 3D shape that I showed you.
Well, I have a question involving like newer theories. So when you are computing the ACE matrix and you found a bound, for example, in the case of quantum gravity, that bound works for every theory that you think of? Or it depends on which theory are you working on, how the bound will look like?
So let me say two things about that. So one thing is that there are two ways of putting bounds. One way is rigorous, like what we are doing. Then it's perfect. When we do something rigorous, it's done. The other is numerical. And when it's numerical, there are two ways of approaching the bound. One is by constructing explicit S matrices. That bound is called the primal bound. And you just ask the computer to construct viable S matrices. And then, the more computer time you spend, the more you explore. All those S matrices that a computer finds, by definition, are good S matrices. They obey all the properties, so they are good. But you never know when you finish. You need more and more computers to make sure that you converge to the optimal region, if you don't have an analytic way of deriving it, like here. The other way is excluding theories. You find ways of saying, this is excluded, this is excluded, this is excluded. So you come from the other side. So you carve out the space, not by including stuff, but by taking out rock, by excluding stuff. And when these two methods converge, you know the bound is optimal. Before they converge, you are not sure. You can still exclude more, or you can still include more, and you go on and go on. So that's the first comment. The second comment is about physics, which is that even if you converge, that was under some assumptions. Then you change the assumptions, you put more assumptions, or you relax the assumptions, and now it moves. But that's a different thing. That's new physics. So when we ask what's the space of theories of quantum gravity, is with some assumptions. We are working in some number of dimensions, perhaps we are imposing supersymmetry, perhaps we are doing a bunch of things, and then we get some bound, and then we try to relax it more and more to approach the real world.
More questions?
So can the theory of S matrices can be used to describe classical waves too?
Can we use the theory of S matrices to describe classical waves? So, well, we should ask Ricardo, but the point is that there are techniques that people use to compute perturbative amplitudes that some people are using now to study the classical limit of those perturbative amplitudes that correspond to more classical amplitudes. Then you have to work out carefully what does it mean to extract a classical part out of a quantum diagram and so on. So there are lots of research being done about when you have a complicated process, like a Feynman diagram, where you exchange many particles and so on, what's the classical part of that diagram and how can we use that classical part to extract things that are related to things that people observe in, say, gravity wave detectors.
The answer is yes.
Yeah. So, more questions? No? Okay, so good luck and